As before, let me get everything sorted here. Um, we will do the last 15-20 minute bit of the virtualization part from yesterday, because we went a bit short on time. I didn't want to rush through it or push anything, so I still wanted to show you at least bits of it. And then from, I would say, like roughly like 20 minutes, then we go to the workflow showcase presentation, and then have like half an hour from 5:30 to 6 for general discussions and questions, everything that you want to bring up and let us know. And excuse me. And then for those interested and have time, we also will do the social. Okay. So to maybe briefly summarize what we did yesterday regarding Docker and images and these things, we briefly explored and learned how Docker works, how we can download images to software containers, how we can use them, and also how we can manage them. The piece of information that's missing right now would basically be how our Docker images or any sort of software container image is being created for specific projects and pipelines. How can it actually install things, and how you can share those images once you have them created. So when it comes to creating Docker images, or basically any type of software container image, there are two parts that are tremendously essential and relevant, or essential for this. First of all, we call the Docker file, which we'll explore in a bit. It's basically a text file describing how your software container, your computing environment should be created, and the things that should be composed of. And then a build command that basically uses this Docker file, this text file, follows the instructions therein, and creates the computing environment specified. So, as said before, the Docker file, and in Singularity would be called Singularity recipe. It's a text file that contains a mixture of build and bash and shell commands. So, being the focus of this part of the section, so we can create one of these files in our directory that we created yesterday. So within our directory that we created yesterday, we can simply create this file called Docker file. And next, we're just going to open it for an initial inspection in the text editor of your choice. I would use Visual Studio Code, of course, because that's the one we're using. So just let me find my text editor. Should be here, but it, oh, sorry, give me a second. Almost. So there we go. So once, if we open it as it is right now, then of course it's empty. There's nothing in there, because so far we didn't specify anything that should be in there. We just created an empty file called Docker file. And now we need to populate it according to the virtual environment that we want to build. Okay, that's the important part. And as said before, the information that we need to provide here in the Docker file for Singularity recipe, that's a mixture of Docker and Singularity specific commands, and what we would call general Linux commands, that if you use Unix-based systems or Linux systems, are rather familiar with. At the beginning of every Docker file is basically the base image, which corresponds to the underlying operating system. Remember the things, with the graphics I showed you, how computing environments are stacked and composed of, starting with the operating system, and then libraries, binaries, applications, and so forth. So, for example, given that or things we're worked on, we might be using the Ubuntu image. The first thing we have to write in our Docker file is this from Ubuntu. I'm just going to copy paste it because I'm also lazy now. And this is all we're going to need to write in here from Ubuntu, basically indicating, telling us, or telling the Docker file that as a base image, as the base underlying operating system, we want to use Ubuntu. We could also specify the version again. And we could also make it a different Linux-based system if we want to, like Debian or what have you. And basically, again, telling from this base layer, we're going to start off going forward. Next, we're also going to specify that the installation of packages, programs, and whatnot will be done non-interactively, so that not every time we create our image, we have to say yes to every little installation thing, which will happen if you specify it accordingly. And really, again, I'm just going to copy and paste this over here. You can do the same if you want to, of course. Additionally, we will also set the encoding startup of our operating system, basically telling our image, okay, what kind of language you want to use, and what kind of language coding, and what should be the entry points, and what would be the startup process, what should be done once our container software image is fired up, ready to run. And then we can already install package libraries, etc., where in most Linux operating systems, this is done through apt-get, a command you will also have explored if you follow the install instructions for this course. And now we'll basically tell our Docker file here, okay, we want to include all of these libraries and binaries. And our complete Docker file looks like the following. Starting from Ubuntu as a base operating system, we want to install it non-interactively. We did a bit of language encoding in our computing environment and specify the libraries and binaries we want to install. And that's actually already enough to build our first Docker container. So if you follow along and also have this Docker file now with that information, what you can do now, or what you do in general, is use the Docker build command that basically looks as follows. You have Docker build followed by a -t, specifying then the image name and pointing to the Docker file you want to use to create an image from. Okay, so and the name for the Docker file or the container, sorry, the name for the container, the software environment that you want to create, that can literally be anything, but should follow common coding practices, and I guess should also be a bit insightful at best. So if we want to do this for our case right now, what we need to run is Docker build -t. I, again, to follow the background joke here a bit in my presentation, we'll call it Millennium Falcon, and then just write a dot, because the Docker file that we want to use to create an image from that specifies the computational environment that we want to create, encapsulate right now, is located in our current working directory. And this dot basically indicates that. Dot means the directory I'm in right now. So if we do that, Docker build -t. Now, of course, you can choose a different name if that's too long, or if you don't like the dollar or whatever. Write that, hit enter, and then Docker starts doing its magic, telling you, okay, I'm at these different steps, because again, remember, these image files, these computational environments that we create are based on layers. So each thing we write in here will be one layer composing the final result and outcome. And depending on your operating system and internet connection, just as yesterday, this might take a while or not. You can see me, it's running like half a minute now. but because we're already installing quite a few packages here, this might take it a bit. But as you can see, only after 46 seconds, it's done. And now what we can do is use the comments we had yesterday already, Docker images, to make sure it's already there. So if we like Docker images, we see Millennium Falcon latest just created a couple of seconds ago, being only 371 MB, and it sucks. So with that, we already created a condition environment, and this image here that we have now could be shared, could be uploaded to Docker Hub. You could use it to run things on your machine. That's really all it's needed. And maybe, I don't know if people tried it, but if you tried it, again, you can just copy paste things from the virtualization underscore comments.sh. From the people who tried it, if any, did it work for you? If so, maybe do the thumbs up. Would be cool to see. And a few key points to remember from this part. A given image that you build, and I see a few thumbs up. Thanks so much, folks. That's fantastic. A given image that you work with can never be changed, right? I said yesterday, if you want to change something, then rebuild a new version of it. And it's necessary to build these new ones in case you have functionalities missing, or you need to adapt things. Imports are essential: the build file, the Docker file, for example, we just did, or similarity recipe, and the build command, with images being composed of these different layers, and the build process basically mirrors, follows these principles, adding components functionality layer by layer, depending on how you specify it in the build file. The build files itself, again, mimic this mixture of Linux system setups and Docker Singularity Linux commands. And again, it's possible to share layers between images, which can speed up the build process and minimize storage. So if you have a couple of layers that are used in different images, these can be reused from the cache, for example, to minimize storage and downloads and things. And while this already is like seeing something like this without having ever worked on Linux-based systems or virtualization, sure, we just copy paste it in some line of code, but it can already seem like an overkill and very complex. But the image we created is super basic. There's really not a lot in it, and we could do a few things, but not a lot. So the fitting compilation of the entire Docker file, if you, for example, want to run an analysis, what have you, for company through pipeline, that is actually very convoluted and prone to errors because you forget things. It can be a lot of try and error, a lot of time searching back and forth, especially if you're new to it and don't have like a stack of things you could reutilize. So you might wonder now, isn't there a more sufficient, faster, and easier way of creating these virtualized environments in terms of a container? Because with sort of Conda, that's comparably easy. Well, for containers, it can be comparably easy using this thing called NeuroDocker, which is, where as it sounds, a Docker image that is there and targets the creation of other Docker images specifically for neuroimaging analysis. So you could call it Docker Captain if you want to. And the cool thing is that the entire thing we just wrote, that appeared as lineup, can be shortened to these lines, which doesn't seem like less lines of code, but it's already way more intelligible because we run a Docker command here using NeuroDocker. And if you want to check the website, it's actually quite nice. It has a few examples of how you can create different Docker containers, for example, using FSL, FNI, FreeServer, ANS, SPM, NiPy. I highly recommend to check that out. But as you can see, what we do basically is that use very, very intelligible and simple arguments to specify the things we completely wrote or here copy pasted because of time and laziness, right? So we can just tell it, okay, as the base, use Ubuntu. As a package manager, use apt, and install all these different libraries, please. And for the example at hand, it might not make a huge difference, but what it actually does is if we run this, so if we were to do this thing here, and for that we're just gonna start a new file. And put it in. Let's call it generate images.sh. And I'm just gonna basically create a little bash script. And once you run that, what's happening actually is that Docker basically writes the Docker file for you. Okay, so instead of you having to write everything yourself and putting all these comments in, painfully looking for it and whatnot, Docker, once you specify the things you want to do, writes this entire Docker file for you of all the specificities, necessities that are in there. And as you can see, these few lines of code are actually extended to quite a bit of something else in there that you would otherwise have to write yourself, which can be very painful and a lot of work. So with Docker, that's made super easy. And we can also directly just save it to a Docker file if we want to, be using this basically Python command saying that the output of this Docker Docker command one should be pasted into a Docker file. Okay, and if we do that, we should get in the end is a Docker file, just as we basically created step by step, but now has all this additional information and is created automatically again from Docker, right? So we get the timestamp saying, oh, this was created by Docker using this version, and then have all the different comments in there used, necessary to creating this computational environment. And the cool thing now is not only did we have this information when it was created with what version, but because we put this thing in a super tiny batch script that we run, this thing itself here, the creation of images, this can be placed under version control again. So when you change the Docker image or the build file accordingly, you can track those changes using simple version control again. It's combining these different aspects, which is super, super useful. So while we have that in there, we know that for our example, we need Python. We need a Python environment, and in order to get that in, it's actually also no biggie, because with Docker, we can actually combine Python virtualization and this bigger virtualization in terms of operating systems using software, images, and containers. So in order to recreate the Python environment that we did with Conda yesterday and put it into our container in a way that it can already be used, automatically be used, we just need to add these few lines of code, -- mini Conda, describing that we want to install Python 3.7 using Conda, and then of course installing DyPy and Fury, the environment's name, it was R2D2 yesterday, and with activate equals true, we tell our Docker file and the image we created from that, once we start the image, that this Python environment should already be activated. So this should be the Python that we are going to use when we operate, do things within the image. So basically, again, just copy pasting this out into our little script that does that for us. If we now rerun this, now of course, sorry, there's a line break. It always indicate line breaks. The write scripts, especially using bash. Then what we can do, using this new Docker file that we have, as you can see now down here, it creates everything necessary. Oh, sorry. It entails everything necessary, and this part's here, to create the Conda environment, the Python virtualized computing environment, installing all the things we want, and making it ready to go in our container. And I don't know about you, but I neither want to write this every time nor copy paste it. So with NeuroDocker, automatically created Docker files, both placed on a version control, and then building things up, very less prone to errors, super nice, and of course reproducible. And if we hit that, then we can see it's actually not starting from the very beginning again, but it's starting from the new point. So from the point where our image changes. So it's not recreating the entire thing starting from Ubuntu, because we didn't change that. The things we changed and added were the Python environment. So it's only starting from this part. Everything else before remains the same, and we can just reuse that, adding the Python things, adding it to our image, and creating a new one. So then again, because it's composed of layers, it's very easy and fast to build up. And again, depending on all the surroundings, it might take a while or not. And now what we can do after this is built, and I'm just gonna stop that here right now because we don't really have time, unfortunately. If we check Docker images, -A, so show me all the images that are already there. We see the different outlines. Now, because we didn't rebuild it entirely, we don't see the thing I want to show you, but once you recreate images over and over again, updating and testing, the previous instances images you have are actually not automatically overwritten or deleted. They remain because reproducibility and computationalized environments. So if we, for example, rebuild the Docker container and update it 10 times, you would have 10 different images on your machine with only the latest one, the last one you built, being correctly tagged in name, and everything else is what's called untagged. So they are basically have the name none, and those are the previous instances of the image. So at some point, if you don't carefully watch out, this will take up a lot of space. You would have to delete these previous images by hand, or just use Docker commands, basically telling Docker, please remove all the images that are not tagged or don't have a name or these things. So and after all this, what we could do now is try to see if our analysis works and do that within our container. So what we would do, and I'm just going to get through this very quickly right now, I'm very sorry, don't have time for it. For example, what you could do is basically map again these paths to make your analysis scripts available inside the container, and then run it again, just using as we did before on our host machines, but now inside the container. But if you were to do that, you would get an error telling you there's a segmentation fault. And the problem with that is that if you use a software container, an image and computation-based environment, by default, they don't have any window. They don't have any screen that they can access to. So if you want to have a graphical user interface, or for example, in our case here, we need a screen, a window to generate our figures that we want to have, this does work by default. We need to set things accordingly. You can either map your host display, so you can map your display of your laptop to be available for the computationalized environment, the container, so that it's basically just using this. But because we don't need anything interactive here, what we can do is using a little Python snippet. I think it's not important to understand the nitty-gritty here, but there are ways to basically create a virtual display in a container that basically allows you to render graphics on or do things. So if you need to do like things in a non-interactive way, you just need a screen to render things on and then save them using a virtual display setup. And this also works with other programs, not only Python, of course. There's this way to do that. And accordingly, we would update our container. And if we would now run this again, basically making our script available inside the container, and then from within our container, running everything again. So you can see our script that we checked out quite a bit yesterday. I'm just going to copy paste and add the things that we need. We now on our desktop or somewhere else run this Docker thing again, docker run -it, -rm for remove from running instances, and then make our desktop and therefore also the script that we worked on available inside the container. And at this point, you might want to use the one I asked you to download, because that's the final version where things are going to run if everything works out. So start up, we're inside our container. And then as we just did in our host system yesterday, using this conda-based things, we can now run things from within the container. And while it does that, because it needs to download data, we can continue and basically check if everything works out in a bit. And what you can do, I can already tell you what will work. And now what you can do is basically save this Docker image. You can share it via USB, other like external hard drives, what have you. But of course, you could also tag it accordingly and use Docker push to push it to Docker Hub and make it available there. Because I did that last week, so make it available for you. And this is where you also downloaded it from. So if you have the option, and it's all good and no problem, I definitely recommend sharing Docker images using Docker Hub, basically just uploading them as shown here, just using Docker push with the corresponding tags, and then it will upload to Docker Hub automatically. And again, all you need is a Docker ID that is free to you. And then you can share your computational environments for others as well. And as also said yesterday, there already has the option to use automated builds. You can combine GitHub and Docker. So if you have a Docker file on GitHub, you can tell Docker Hub to use this repository and the information therein. So whenever there's a new change, a new push, a new commit, and the Docker image is automatically rebuilt. So every time you change something on the Docker file, it is on a version control, it's just suggested, the Docker Hub will automatically fetch this information and rebuild the image for you in the cloud, so you don't have to build it locally and push it up again. However, as I said before, this is super customizable and free, but you have to apply for it because they recently changed that to only paid plans. But if you're working on research, you can still use it. You just need to tell Docker, please let me do it. And with that, I just want to briefly provide a quick summary saying that, sorry, also like for rushing through this, but we don't have the time, unfortunately. All of this session was meant to show you that virtualization is a very, very powerful tool if you share code, scripts, functions, pipelines with colleagues, other people, whoever. You don't have to deal with all the dependency issues, except of course, getting the virtualization software itself to run. And you can automate large parts of your processing. For example, you can have different virtualized environments, computational environments for pre-processing your data, for statistical analysis, everything at once, what have you. And you can rerun analysis with identical or slightly changed parameters to see how stable things are. And while there's a very, very steep learning curve, especially in the beginning, of course, once you get a hang of it, just start using, and this is really my gift to you there, is that whenever you start a new project, try to use virtualization, make a content environment for it, if you want, and have the means to also make this computation, these containerized environments that you can do everything therein, so that also your future self doesn't need to worry about any like software dependency issues and what have you. And if we were to compare all these different things in terms of pros and cons from virtualization started, that's very straightforward, lightweight, works across all platforms. Con is that it's really restricted to Python, the adjacent things. Sharing cross-platform is limited because there are Python things that just don't work on Windows and so on. It's no graphical user interface. If you work with containers, you can share the entire operating system via the dedicated infrastructure being the container. You can have complex environments and use version control for your build and files. They are comparably lightweight and fast, and also work across the platform and high-performance computing clusters. So with that, you can really, for example, try things on your Windows laptop working in a container that runs Ubuntu, for example, and then send it off to a computing cluster that just runs the exact same computational environment analysis therein. However, we have this deep learning curve. We can reintroduce dependencies if we don't really watch it for it, and also don't have a graphical user interface. With virtual machines, that's being one of the pros. You have a graphical user interface. Maybe that's at least in the beginning, it's easier. Works cross-platform, can have complex environments and shared entire operating systems, but they're super heavy and slow, inefficient, and you can't use them in high-performance computing clusters. And version controlling them, as far as I know, also is not really working. So with that, we also have further reading, because we know it's a lot and it's a very different way of working with things. We compiled this nice list that you find on the slides. That's also on the website, just linked below the slides. And in the end, we also added a few notes on Singularity, just to show that Singularity works very similar to Docker. It's just that some of the comments you might want to use are a bit different, sound a bit different, but that's really all there is.